So my wife and I are out on a little picnic today, and we made a new friend.
2,000 miles. 2,000 miles.
Alright, so today we're looking at section 13.3, which is all about independent and dependent events. So what's the difference between independent and dependent events? Well, we say that events are independent events if the occurrence of one event does not affect the probability of the other. We say events are dependent if the occurrence of one event affects the probability of the other. And lastly, we have what's called conditional probability, which will look like this. P, so we're going to take the probability of event B given that A occurs. So that bar right there means given that. And we have our two events, A and B, B and A. We're going to say that event B occurs given that event A already has occurred. So conditional probability is a probability that has conditions attached to it. One thing has to occur before the other one, and that is critical to dependent events. Events that occur where one event affects the probability of the other. Independent, you have two separate scenarios. One doesn't affect the other. Dependent, one does affect the other. And we'll have to calculate this conditional probability. Let's start with the easier ones, independent events. So for independent, the probability of independent events, we're going to say that if A and B are the events, it could be whatever, if A and B are independent events, then the probability that event A and event B will occur is equal to the probability of event A occurring, and we multiply it by the probability of event B occurring. So we're going to calculate each of these probabilities individually and then multiply them together. So let's look at an example. Say that given the spinner to the right, so this guy right here, what is the probability that you spin a 1 and then a 4? Now we have to think about this. I want to spin a 1 and then a 4. Now, would this be independent or dependent events? Well, obviously they're independent because it's in this section, but the reason is that once I spin my spinner, wherever it lands after I spin it, that doesn't affect my second spin. So I'll spin it, it'll land right here, and once I spin it again, that's a completely new situation. Basically, think about before the second event, if everything resets, then that's independent events. So once I spin my spinner, it lands right here, everything's resetting, and it has no effect on my second spin. So to do this, I'm going to say what's the probability of spinning a 1 and then a 4? Well, it's going to be equal to the probability of spinning a 1 times the probability of spinning a 4. Well, what's the probability that I spin a 1? Well, I have a total of 1, 2, 3, 4, 5, 6, 7, 8. So remember, probability is what you want over the total. So I have 8 spaces total. I'm looking for a 1. I have 1, 2, 3. I have 4 spaces, 4 sections out of the 8 that are 1s. So I'm going to multiply that to the probability that I get a 4. I still have 8 total sections, and I have 1, 2, 3. 3 out of the 8 spaces are 4s. So I multiply them together, and remember when we're multiplying fractions, all I'm going to do is multiply the top to get 12, and then multiply the bottom to get 64, and that is going to reduce to 3 over 16, so 3/16. Now another way I could do this to make it maybe a little bit easier is let's reduce before I multiply. So I have 4/8 times 3/8. The 4 and the 8 cancel, that's a 1 and that's a 2. So now I multiply the 3 and the 1, I get 3. 8 times 2 gives me 16. So 3/16. So that is my probability that I'll spin a 1 and then a 4. Question 2. There are 5 marbles, so you're going to have a bag here. Inside your bag, you have 5 red marbles. 1, 2, 3, 4, 5. We'll have 7 blue marbles. 1, 2, 3, 4, 5, 6, 7. And we'll say we have 8 cat's eye marbles. 1, 2, 3, 4, 6, 7, 8. So what's the probability that you draw 3 cat's eyes marbles in a row if you replace the marbles after drawing them? So this word replace is actually really important, because what this means is that after I pick one of these marbles, let's say I get a blue one, after I take that out and get my blue, I'm going to put it back into the bag, and the total amount of marbles stay the same. So to do this, what we're going to be looking at, and this replace makes it independent. We're going to say what's the probability of getting a cat's eye, and then another cat's eye, and then another cat's eye marble. Well, it's going to be equal to the probability of getting a cat's eye times the probability of getting another cat's eye times the probability of getting another cat's eye. Well, what's the probability of getting just one cat's eye marble? Or a total of marbles, we have a total of 20 marbles in the bag. And how many cat's eye marbles do I have? We'll have 8, so it's 8 out of 20. So I'm going to do 8 over 20 times 8 over 20 times 8 over 20. Well, it also reduces. I can divide by, so let's divide by 2. That'll give me 4/10 divided by 2. 2/5, so I could just divide by 4. 2/5 and 2/5. Well, 2 cubed is 8. 5 cubed is 125. So the probability that you get 3 cat's eye marbles in a row is 8 over 125, and that would be your answer. And this is all because we're replacing them, so that makes it independent, because the total, every time you replace the marble into the bag, it resets the whole system. So that's the key, is does it reset the system? Now we're going to say that events are dependent if one event affects the probability of the other. So for example, let's say that we had 2 lemons and 1 lime in a bag. So 2 lemons, 1, 2, and 1 lime. Obviously we don't know where they are in the bag, but let's say that you pull 2 pieces of fruit out, and every time you pull the piece of fruit out, you do not replace the fruit. Do not replace. Well, every time you do not replace a piece of fruit, well, that's going to affect your next piece that you pull out, because the total's changing, the types of fruit you have in there change. So this is dependent because every time you pull out a piece of fruit, everything changes. Nothing resets. So when we look at this one, we could do a tree diagram to show this. And how this works is, let's say you pull a piece of fruit out of the bag, and the first one you get is, well, what's the probability that you get a lemon? We have a total of 3, so 3 total. So the probability that you get a lemon is 2/3. Because we have 2 lemons, and there's 3 total, 2/3. Well, on your first pull, what's the probability you get a lime? Well, that's 1/3. Let's say let's assume that you get a lemon on your first pull. Well, what's the probability that you get another lemon? Well, since I already pulled out a lemon, we take one away, and so now the probability that I get another lemon, well, what's my total? My total's changed to 2, and there's 1 lemon in there, so now it's 1/2. On the same token, what's the probability you get a lime? Well, it's still 1/2 because there's only 2 left, 2 pieces of fruit left, and one of them is a lime. Let's go down this branch. I still take, let's see, I still took away a piece of fruit, but now we're assuming that I pulled a lime first, so I'm going to take away that lime, and now what's the probability that you'll get a lemon, assuming that you initially pulled out a lime? We'll have 2 left, 2 pieces of fruit left, and both are lemons, so the probability that I pull a lemon on my next pull is 1. It's going to happen. What's the probability that you pull another lime? Well, that's impossible, so it's going to be 0. So to calculate these probabilities, we're just going to multiply them together just like we did for the independent events. We're still going to multiply it together. So this probability, we'll say probability of lemon is going to be 2/3 times 1/2. Well, 2/3 times 1/2 is 2/6, which reduces to 1/3. Well, what's the probability that you'll pull a lemon and then a lime? Well, that's 2/3 times 1/2. That's still 1/3. Probability that you'll pull a lime then a lemon. What's 1/3 times 1? That's 1/3. What's the probability that you'll pull a lime and then another lime? 1/3 times 0, which is 0. That's not going to happen. So that's how you calculate those dependent events. Now what we were doing, and I didn't really say anything about it, but in order to find the probability of dependent events, we were using conditional probability. So conditional probability is where you have P of B given that A occurs. So going back to this, we're assuming that one event occurs before we calculate the probability of the other. So when I was looking at these, let's say this top row here, the second event, of pulling the second lemon, I was assuming that I already pulled my first lemon. So that's a conditional, this one right here, that probability is a conditional event because I'm assuming the first lemon was pulled. So we say that the probability of dependent events, we're going to say if A and B are dependent events, then the probability of A and B occurring is the probability of A occurring. That's the first event that will happen. And we're going to multiply it by this conditional probability, the probability that my second event occurs given that A already did occur. So we're going to assume that one event does occur. Let's look at a few examples and note that these examples, next 3 examples, are in the textbook, but they're not in your notes, so refer back to the textbook if you want to review that section. But you guys don't have to write this down, just listen to the explanation. So for this, we say we have 2 number cubes are rolled, so just think 2 dice, one is red and one is blue. Now explain why the events are dependent and then find the indicated probability. So example A, what's the probability that a red cube shows a 1 and the sum is less than 4? So we have two events occurring here. We have a red cube showing a 1, and our second event, event B, is that the sum is less than 4. So the book has two steps. Let's first calculate, we'll call this probability of event A. And that is a red 1. So what's the probability that this first event, rolling a red 1, occurs? Well, we have a total of 36 outcomes here. If you were to count these up, 1, 2, 3, 4, 5, 6, and we have another 6. So 6 by 6, there's a total of 36 outcomes. Well, how many red 1s do we have? We only have 1, 2, 3, 4, 5, 6 red 1s. So 6 out of the 36 are red 1s. So that probability of event A occurring, which is the red 1, that's 1 out of 6. Well, now let's calculate my second event. Well, this is the conditional event, B, given that A occurs. Well, now we're going to say what's the probability that the sum is less than 4, given that we rolled a red 1. So when we look at this, not only do we have to have a sum which is less than 4, but we also have to have a red 1. So really what's going on is that I'm getting rid of, because a red 1 has to be rolled, I'm getting rid of all of these here. So ignore all those, I'm only going to look at everything with a red 1, which is that top row. Well, out of those, how many of those have a sum that is less than 4? Well, this sum doesn't work because that's 7, 6, 5, 4. So I'm left with only those two. But remember our total, because I'm starting with only this top row, because you're getting rid of anything that doesn't have a red 1, so our total was 6, and out of that 6, only 2 were less than 4, the sum, which reduces to 1/3. So that's the probability of our conditional event here. Well, now to calculate the total probability of the stated question, we're going to, step 2, find the total probability, and this is our dependent probability. What we're going to do is, so we're saying the probability of a red 1 and the sum is less than 4. This is event A, event B, and here's event A, conditional event here. Well, I just take both of these and multiply them together, so you get a 1/18. So that is the conditional, or the dependent probability there, of rolling a red 1 and the sum being less than 4. It's 1/18. Example B, I suggest pausing the video, trying this on your own, just get a piece of paper, see if you can figure it out. But this question states that, what's the probability that a blue cube shows a multiple of 3 and the sum is 8? So event A is that you have a blue cube that shows a multiple of 3. Event B is sum is 8. So let's look at our first event, which is a blue multiple of 3. Well, how many, look at all my combinations here, my outcomes, they all have a blue cube. Which of those blue cubes have a multiple of 3? Well, that gives me these blue cubes have a multiple of 3, 3 times 1. And then these as well. 3 times 2 is 6. So we have a total of 36. And out of that 36, how many blue cubes show a multiple of 3? Well, we have 6 and 6, that's 12. So 12 out of 36, which reduces to 1/3. So that's event A occurring. Now let's look at our conditional events. Event B, given that A occurs. To do this, we're going to say that out of those, so basically what we've done is gotten rid of these. I'm going to ignore these now. Just delete those. Now my total is only going to be those two columns. Those box columns. Well, out of those two box columns, the multiples of 3, how many have a sum that is exactly 8? Well, 6 and 3, 9, that doesn't work. 5 and 3 is 8, 7, 6, 5, 4, 12, 11, 10, 9, 8, and 7. So 2 out of those 12 work, which reduces to 1/6. And now to calculate the probability of this whole thing occurring, the multiple of 3 and the sum is 8. You take event A, which is a blue multiple of 3, our conditional event of B occurring given that A occurs, multiply them together, and we get 1/3 times 1/6, which gives me 1/18. And that is your solution. Now lastly, how do we determine whether events are independent or dependent? So you have some questions where it's not stated whether they're independent or dependent. How do you figure that? Well, to do this, we already did this question before, where we had the bag of marbles with the 20 marbles, 20 marbles, and we had we drew 3 and then replaced them back in. So remember that replace made it independent because you reset everything. Well, let's say in this example here, example B, what's the probability that you randomly draw 3 cat's eye marbles in a row if you do not replace the marbles? So now, since we do not replace them, we will not be resetting the system. The one event actually affects the second one because you're changing the total. So to do this one, so this is dependent. We're say 3 cat's eye marbles in a row, so C, C, and C. Well, now we're going to say the actual notation is going to be really long because you're going to do P of event A times P of event B, given that A occurred, and then probability that C occurs, given that A and B occurs. But what we're going to do, pretty simple, is just look at what we want. Remember, want over total. So all we got to do is take the total amount that we want, which is the cat's eyes. So initially I have 8 over 20. That's the probability that I pull 1 cat's eye marble. Well, assuming, remember with our conditional and dependent probabilities, we're going to assume that we actually get what we want. So assuming I got it, how many cat's eye marbles are left in the bag? Well, 7, because we're assuming I pulled it out. Well, how many total marbles are left? Well, 19. So that's the probability that I pull a second cat's eye marble. What's the probability that I pull a third? Well, how many cat's eye marbles are left? Assuming I pulled the first 2, well, 6 out of 18. Well, then I'm just going to multiply them all together, and that is going to give me 14 over 285 after reducing. So that's the probability that you pull 3 cat's eye marbles in a row if you do not replace them. So all you do is just reduce it by 1. Example 3, from a regular deck of cards with no jokers. So if you don't know, it means there's 52 cards in the deck. What's the probability that you pull 2 hearts without replacement? So without replacements, there is no resetting. It will be dependent events because you're not replacing the cards. So what's the probability that you pull 2 hearts without replacement? Well, if you look at your deck of cards, there's 13 of each suit. So that means you have 13 over 52, but we're not replacing it. So assuming we pulled a heart, that means there will be 12 hearts left in the deck, but only 51 cards total. So when I multiply those, that will give me, after reducing, and the way you could do this is you have 1/4 times 4 over 17 when you reduce, and that will give you 1 over 17. Now what if we do replace it? So this will make it independent. The probability you get a heart and a heart is going to be equal to 13 out of 52. Assuming you pull the heart, you put it right back into the deck, you reset everything, and multiply it by 13 over 52, and that will give you 1/4 times 1/4, which is 1 over 16. So that is how you calculate independent events. Now next question states that we have a table and it shows the approximate distribution of votes in Texas. Texas's 5 largest counties in the 2004 presidential election. Find each probability. So example A states that a voter from Tarrant County voted for George Bush. Now before we do any of this, what we need to do is calculate the totals here. So what we're going to do is add up this whole row, add up this whole row, add up this whole row. I guess should say column. And we'll add this row, add this one, add this one, add this one, and this one. And then we calculate the total number of votes, which is 3,125,000 total voters, because this is in thousands. Now, what this is saying is, let's calculate the probability that a voter from Tarrant County voted for George Bush. So what we're going to do is go to Tarrant County, and we're going to go to the George Bush column. So we're going to take that 349. So that's let's see, B given A. So we're going to say you have to be, the condition that must be met for this conditional probability is that they have to be from Tarrant County, and then vote for George Bush. Well, that's 349. Well, what's our total? Well, the total is from Tarrant County, what is it? 559,000. So we do 349 divided by 559, and that gives us 0.624, which is the probability that a voter from Tarrant County voted for George Bush. So notice that the total here was only Tarrant County. That was our total. That's all we cared about. Well, now let's go ahead and look at example B. We're going to say that a voter voted for John Kerry and was from Dallas County. So notice that our total has changed because now we're going to be looking at the total number of voters. So we're just going to worry about the voters. So not only do they have to vote for John Kerry, but they also have to be from Dallas County. So first let's calculate the probability that they voted for, or that they're from Dallas County, given that they voted for John Kerry. Well, to do that, we're going to say right here, look at that row. So we get 336 over 1422. So that 336 is the total number of voters from Dallas County that voted for John Kerry. So we're taking the Dallas County portion of the total. Our total here is the total voters for John Kerry. We're going to calculate that probability first. Now, after we do that, then let's calculate the probability that anybody voted for John Kerry. So for that one, we're going to take, out of all the voters, we're going to take the John Kerry portion, that 1422, out of the total voters, all of them, and calculate that probability. So that is where the 1422 over 3125 comes in. But we still have to multiply by our conditional probability that they were from, they voted for John Kerry from Dallas County. Now we multiply those together, and that gives us 0.108, which is the probability that a voter voted for John Kerry and was from Dallas County. Alright, if you guys have any questions, shoot me an email. See ya.